let's start, like we often do, we'll start with the problem. So given the following, del cross, and then there's this function. The first entry is yz plus r tangent z. Second is z e to the y. And the third is some unknown function. It's a multivariable function which depends on x, y, z. And this del cross, we have a name for that, and that is called the curl. So we're taking the curl, and we know the output. Z squared minus 1 e to the y, and negative z. And the question is, find a possible function for p of x, y, z. So I know, essentially, the output, and I want to find what's the possible function. Now, the way we should be thinking about what's going to happen here before we start this problem is when we see del, we should be thinking, oh, that's acting like a derivative. So in some sense, what's happening here is like I'm giving you information about the derivative, and now I'm going to ask you, can you tell me about the function it came from? So one of the things you'll notice is it doesn't say find p of x, y, z. It says find a possible p of x, y, z. The reason why we put in the phrase a possible is when we take derivatives, we lose information. And so the classic way of thinking about this, if we were thinking with our Calc 1 hats on, we would say, oh yeah, right, because there's a plus c. So we don't have enough information to determine it precisely. We'll see that there's a little bit more than plus c going on, but that's all right. We'll get there when we get there. So this is a good chance for us to review. Okay, so del cross. So the way that we do the curl, or at least the way I like to do it, because it's the easiest thing for me to remember, is to remember the process. So I'm going to take a 3 by 3 determinant. So I have I, j, k. The vectors fill the first row. The partial derivatives, these operators, fill the second row. So derivative with respect to x, derivative with respect to y, and the derivative with respect to z. The last comes from the pieces of the function. So yz plus arctangent of z, that's the first entry. Z e to the y, that's the second entry, and the last entry is the p. And I'll just abbreviate p now as just p, but I'm going to keep in mind that p is a function of x, y, and z. So there we go. We need to take this determinant, and we do it like we do any determinant. So we have I partial y, p. So that's going to be p sub y in the I direction, because that partial y of p. Then j partial z of yz plus arctangent of z. So I want to take the derivative of yz plus arctangent z with respect to z, and so that's going to give us y plus 1 over 1 plus z squared in the j direction. K partial x of z e to the y. Well, there is no x, and therefore that derivative is going to be 0. Gone. But I'll go ahead and write a 0k just so I feel good that I didn't forget anything, because I oftentimes forget stuff. Now we're only halfway done. We got to go in the other direction as well. So, okay, going in the uphill direction. And by the way, if you prefer doing your determinants by cofactor expansion, that's great. It works just as well, just as long as you make sure you have it down. So in the other direction, so going in this way, I'm going to have partial derivative with respect to y, yz plus arctangent of z. Well, now when I take derivative with respect to y, well, here the arctangent of z goes away, and what's left is just z, and that's in the k direction, and I got to subtract it. So minus z times k. Then we go to the next one. Z e to the y partial z of I. So that says take the derivative with respect to z of z e to the y. Okay, well that's not bad. That's e to the y. And that's in the I direction. So we're going to subtract e to the y in the I direction. And the last one is we have p partial xj. So that's the derivative of p with respect to x in the j direction. And because we're in our subtracting phrase, we subtract p sub x and j. So if we group this all together, we'll get p sub y minus e sub y, comma, y plus 1 over 1 plus z squared minus p sub x, comma, negative z. So that's just going through and taking the curl. So we've now taken the curl, and what we want is we know what the answer should be. So we're going to compare our answer. So we want this to be equal to, well, on the first term, let's go ahead and expand it. That would be z squared e to the y minus e to the y, comma. In the second term, it'd be y. And the last term should be minus z. So there's a couple of things going for us. We take a look and we say, hey, that last entry, that's looking pretty good. It matches. So, woohoo! We'd be in trouble if it didn't match. The middle entry, the y's match. That's a good sign. The minus e to the y's match in the first entry. But then there's other pieces. We say, okay, what needs to be true? So, gathering what needs to be true, from the first entry, what can we conclude? Yeah, so we need to have that p sub y should be equal to z squared e to the y. From the middle entry, what needs to be true? Yeah, so we need this piece right here, this 1 over 1 plus z squared minus px has to go away. So we get that p sub x has got to be equal to 1 over 1 plus z squared. So we started thinking about, okay, let's just sort of think about what should be true. What we're looking for is some function which has all of these properties. Now, what can we do? Well, we can sort of say, okay, suppose I integrate with respect to x, this second term. If I integrate 1 over 1 plus z squared with respect to x, what would we get? Yeah, because with respect to x, 1 over 1 plus z squared is constant. And so it's like integrating a constant with respect to x. So we say, okay, it looks like we should have 1 over 1 plus z squared times an x. Okay, that seems like it should be a piece of it. All right, how about over here? If I integrate this with respect to y, what would I get? Yeah, if you integrate z squared e to the y with respect to y, you would say, okay, it looks like another part should be z squared e to the y. And now we say, okay, well, are these compatible? Well, in some sense, yes, because this piece right here has nothing to do with y. So when we take its derivative, it'll go away. And this piece, this z squared e to the y, has nothing to do with x. So when we take its derivative, it goes away. And so we can conclude the following, that really we can put these together and say, okay, I can have p be z squared e to the y plus x over 1 plus z squared. Now, is that the only function that works? What else could we do? We could always add a number. We can always add like a plus c. Could we do anything even more exotic than adding a plus c? Yeah, anything with the z. So I could add, if I wanted to, plus stuff with z. Because there's nothing that forbids it. Because when I take the derivative with respect to x, or I take the derivative with respect to y, anything that's in here, this stuff with z, disappears. So that's why we say, okay, well, so we need a possible function. And so the answer is just go with the simplest one. So we go with that one. Now we're going to go through and do this process again in our next session. So this sort of shadows things to come. So this process is going to become a little bit familiar. A little bit. But first, we've got to do today. So what's today? Well, we want to be talking about integrals. We're going to go back to one-dimensional integrals and say, okay, what are they? Well, let's start Calc 1. And when we did Calc 1, we had this notion of this integral. So we said, okay, suppose I want to find the area below a curve, y equals f of x, which is above an interval from a to b. And I said, okay, well, we write that as the integral from a to b of f of x dx, and life was good. What we want to do is we want to take this idea and move it into a higher dimensional setting. So we're still going to be doing a one-dimensional integral, but somehow putting it into a higher dimensional space. So this is what our goal is today, is to talk about line integrals. So here's how we're going to think about it. We're going to think about it, instead of having our interval from A to B, which is this segment here, we're going to make it a curve. So I have this curve. So instead of integrating from A to B, I'm going to integrate along the curve. Now I also need to talk about a height. So my height originally was my function f of x. So what's the height going to be? Well, the height is going to be some function where for every point on my curve, I'm at a point. So now a location is not simply a single number, it's a coordinate. It's an x comma y. So the height will be determined by some function of x comma y. So it's I'm going up to a surface, z equals f of x comma y. So one of the things you can think about doing is it's like we took this sort of flat thing and we're sort of picking it up and sort of curving the bottom and then setting it into a higher dimensional setting. Another way you could think about this is you can imagine that you have some sort of draping that you have to find the area for, and it's on a curved wall. You say, okay, well, I have to say, what's the total area? I go over every point and I say, what's the height up to my drapes? And that can find us the area. Now, be careful here, because you look at this and you say, wait a second, shouldn't this be multivariable? Shouldn't this be a two-dimensional type integral? And here's the clue. And this is going to be a useful clue going forward, because we're going to be talking about these things, is you do a count. You say, how many integral signs do you see? And how many integral signs do we see? You see one. So the number of integral signs that you see corresponds to the dimension of what you're working with. So we're working with a one-dimensional thing. Don't be fooled by saying there's an x and a y there. It's truly a one-dimensional thing. Okay, so how do we actually do it, though? So you might say, okay, let's start with a couple of things. Up here we had this dx. And our dx was a change in x. Here we have ds. Well, what is ds? Well, ds is a change in arc length, because we're just moving a little bit along our bottom curve. So we're on C, we move a little bit. Now, the question is, do we know how to find the change in arc length? Do we? Have we done that? The answer is we have. It's that formula we learned. In fact, this goes all the way back to Calc 2. We learned this, and we did this again at the beginning of this semester. We said that our arc length is approximately the square root of x prime squared plus y prime squared. Now, what are x and y here? X of t, y of t. That's our parametrization. Okay, so we have our curve, which is parameterized by x of t, y of t. We have that the length of a little piece is given by that. And therefore, if I want to find this integral, we say the following. The integral along the curve of f of x, y ds says, okay, break my integral up into little pieces. So what's happening here is I'm really breaking up my time into parts. And as you break time into parts, you'll break your curve up into parts. Now, they don't necessarily all have to be the same length, because what you're doing is you're breaking up time, and you could imagine that on some parts of the curve you're moving slowly, and on other parts you're moving quickly. So as a consequence, it's oftentimes not the case that your points are equally spaced, but that's not going to matter too much as we go in the limit. So we say, okay, we've broken our up into little pieces. For each little piece, we have the arc length downstairs, and then the height upstairs. Well, what do we mean by x sub I, y sub I? Well, it really is what happens when you plug in that time piece into your curve. Okay, so that's what we get. We get this sum, f of x sub t, y, t, then we have the square root, x prime, t squared, y prime of t squared, delta t. And therefore, when we're talking about an integral along a curve, That's what it translates into. So when we talk about this integral f of xy ds on the curve, we rephrase it in terms of our parameterization. So if we're going from a to b for our parameterization, our integral goes a to b, f of x of t, y of t, and then the square root of x prime of t squared plus y prime of t squared dt. Now there's one thing to note, which is what's the right parameterization? Because oftentimes we may not be given a parameterization, we have to pick one. And so how do we know which one to pick? And the answer is you look at the problem and it doesn't matter how you move along the curve. As long as we move along the curve, we're still going to be computing the same answer. So it doesn't really depend on our parameterization. So in some sense, when we're talking about integrating along the curve, we can just say, oh, there's this curve sitting here in space. That's independent of how you moved on it. So given that that's the case, you should always look for what's an easy way to move on the curve. You look for the simplest one to work with, and that's going to be the one we're going to look for. All right, so that's the idea. Now, you'll notice there's a little bit of a caveat here, which is we've got a square root to work with. And square roots are tricky. They have not become less tricky. They have always challenged us. They will continue to challenge us. So be careful. You have to learn to work with the square root. We will see that there's a beautiful case where we can get rid of those square root terms, and we're going to get to that by the end of today. All right. So let's work through an example. Find the integral on the curve of x squared y ds, where our curve is the following. 3 cosine t, 3 sine t, where t goes between 0 and pi halves. Now you might recognize this curve. Have you seen a curve that looks like 3 cosine t, 3 sine t? Well, it's a lot like the unit circle, but the 3 does what? Yeah, it expands the radius. So what's happening here is this is actually part of a circle with radius 3. Now the reason I say part of a circle is time only goes between 0 and pi halves. So what's going to happen is you start at time 0 here, and you're moving in the first quadrant, you end at time pi halves there. So this is our curve. It's our 1/4 of a unit circle. So what do we need? Well, if you come back here, sort of the big part is we need our ds terms. We're going to put a lot of time into ds. We'll talk about their x of t, y of t in just a minute. But let's figure out our ds term. So our ds term is going to be the square root of x prime squared plus y prime squared dt. So let's take our derivatives, the square root. What's the derivative with respect to x? Or sorry, what's the derivative of x with respect to t? -3 sine. So we're going to have -3 sine of t squared. Okay, go to y. What's the derivative of y with respect to t? 3 cosine. So we'll have 3 cosine t squared dt. Now, when you square that out, you're going to get square root. Well, both terms have a 9, so you'll get 9. If you pull that out, you'll get negative sine squared, which is the same as just sine squared. Then over here you'll get cosine squared, which is, well, it's actually just cosine squared. And what happens? Yeah, it becomes beautiful. The sine squared plus cosine squared becomes 1. The square root of 9 becomes 3. So you end up with 3 dt. Which is a nice way of saying that because of this particular parameterization of the unit circle, in some sense what's happening is you're moving along the unit circle at a very nice, steady pace. That's what's being reflected here. You're moving along at essentially a constant pace with regard to location. Okay, so here's the thing. When you're ready to do your translation, when you figure out that one little part, you say the following. Or you say, okay, so the integral along the curve of x squared y ds, you do the following. You change your bounds to your t bounds. So that's going to become 0 to pi halves. Everywhere where you see an x, you replace it by what is x of t. So in our case, our x is 3 cosine t. So this x squared becomes 3 cosine of t squared. Everywhere where you see a y, you replace it by what your y of t is. In our case, y is 3 sine of t. So that becomes 3 sine of t. And where you see your ds, you do the computation, and it turns out, in our case, it's 3 dt. So there's our integral. Now, it turns out this is very 3. You have a 3 squared and another 3 and another 3. So that gets you up to 4 3's, which if you multiply that together gives you 81. Then you get the integral from 0 to pi halves of cosine squared t sine t dt. Now, how do you actually do this integral? You use substitution. What's the substitution to make? Cosine. Yeah. So if you let u equal cosine, what will du become? Negative sine. So negative sine t dt. So we'll end up with, because of that negative, we'll get negative 81 integral, and then we'll get u squared du, and then we have to update our bounds. So when t equals 0, our lower bound, what does u equal? 1. When t equals pi halves, our upper bound, what does u equal? 0. Now, we could flip our bounds, but we don't have to. We can just integrate it. That's perfectly fine. There's nothing that says you can't just integrate. And so if you do, integral of u squared, 1/3 u cubed. So you'll get negative 27, because I can divide 81 by 3, u cubed, evaluated from 1 to 0. When you plug in 0, you get 0. Subtract, plug in 1, well, you get negative 27. So you get 0 minus minus 27, or simply 27. And that's our answer. Okay, so that's an example of a line integral. So it's actually not so bad if you think about what's happening. So we translate in terms of the parameterization. You got to figure out what your ds is, which is fine. You do the work, square root of x prime squared plus y prime squared. And then the other thing is you have to make sure you set your bounds to what your parameterization is. Everywhere you see an x, replace by x of t. Everywhere you see a y, you replace that by y of t. And life is good. Now you might be saying, okay, that's great. Could we do something similar in higher dimensions? And the answer is yes. So you could have a curve that's some high dimensional object. So a curve that's moving through space. And that curve that moves through space, you can think of it as being parameterized by some curve. And you say, okay, well, given that that's the case, can we still do a line integral? And the answer is still yes. The only thing that happens, now you have to replace any x, y, and z with the appropriate thing, and your arc length has an extra term. But the philosophy is the same. Now, you might be saying, okay, but how can we interpret such a thing? Well, one of the easiest ways to interpret, which I think people are comfortable with, is you can imagine that parameterized curve represents, say, a wire in three-dimensional space, and our function might represent some sort of a density. And now, what we're doing is when we integrate the density, we're finding mass of a wire. So that's okay. So these integrals can be interpreted in a way that's reasonable. All right. So let's find another example. Suppose our curve, cosine t, comma sine t, comma t. And t goes between 0 and 2 pi. Have we seen this curve before, cosine t, sine t, comma t? Suppose I just covered up the comma t on the end. Cosine t, sine t, what does that do? That's the circle. It's a unit circle. So the cosine t, sine t, if it was just the xy plane, would just be going in a circle. Now, there's that t component. The t component says as time moves forward, you move up. So what happens is you circle and you move up. So what shape is that? That you're circling around but moving up at the same time? It's a helix. So this is the helix. So do we need to know that? No. But you know, it's fun to know stuff. So what's happening is this is the helix, and it's, if you look at it, essentially it's one circling around. So it'll start here, and then it's going to circle around, and then it's going to end up back here, directly over where it started before. It's just moved up by 2 pi. So I've moved one revolution around. Okay, so we need to go through and do our pieces. So let's handle this last part on the end. So this part, remember, is our ds. So if I want our ds, that'll be the square root of, well, derivative of cosine, negative sine, and then we're going to square that. Derivative of sine, cosine, and we're going to square that. And derivative of t is 1, and we'll square that. And of course we get the same sine squared plus cosine squared being 1. 1 plus 1 makes 2. So we get square root of 2 dt. And you're probably thinking, wow, these are all nice. Well, yeah, because we're doing circles. Circles are nice. We're going to do examples which are not circles, and then we'll definitely break you of the belief that all things are nice. So, but that's to come. That's to come. Spoiler alert, it's coming. Okay, so now we do our integral. So the integral along our curve of z plus x ds. So instead of saying along our curve, we're phrasing everything in terms of time. So it becomes the integral from 0 to 2 pi, because that's our time. Where we see a z, what do we put? We put t, because that's our what z is in terms of t. Where we see x, what do we put? Cosine t. So t plus cosine t. And where we see a ds, we put what we computed. It becomes square root of 2 dt. And now, this is not so bad. The square root of 2 is a constant. The integral of t, a half t squared, or t squared over 2. Integral of cosine of t, positive sine. And now we're going to evaluate from 0 to 2 pi. Well, if you plug in 2 pi, you'll get square root of 2, and then you'll get 1/2 times 2 pi squared. Sine of 2 pi? Sine of 2 pi? So sine of 2 pi will be back to 0. It's the same as sine of 0. Okay, subtract. What happens when we plug 0 in? We'll get 0, because sine of 0 is 0, and 0 squared is 0. 0 squared is 0 even after we multiply it by half. It's really hard to recover from 0. All right, so if we clean this up, well, when we square 2, that'll give us 4 times half is 2. So we'll end up with 2 square root of 2 pi squared. And that's our answer. Okay. Well, as I've mentioned, we can use parameterized curves to model wires. So we're going to do that. So let a wire be bent to form the top half of a circle radius. I promise that not everything will be circles. It's just that's the circles make it really easy with the ds. We'll do an example where it's not a circle. But for now, a wire is meant to form the top half of a circle of radius 2. So we're going to think of this in the xy plane, mostly because I see here this is a function of x and y. The top half, I'm going to be up here, and I have a circle of radius 2. So here's my wire. Now, this has the property that the density of the wire, the density at any given point is y. What does that mean about my wire? Well, it means that near the axis my wire is very thin, but as I move up, I'm going to get thicker. So I'm very thick at the top, and then very thin at the bottom. So the wire is definitely a lot thicker near the top part here. Okay, so the question is, where's the center of mass of the wire? Now the good news is we can find part of the center of mass pretty quickly by symmetry. What's true about the center of mass? The center of mass has to respect symmetry, and there's a symmetry here along the y-axis. So we know the center of mass has to have x bar equals 0. All right. Well, what's next? We got to find the y bar. And here we can't just use a picture. There's not just symmetry. We've got to do the work. So we'll do the work. All right. So the first thing to decide is what's the parameterization to use. Now, you're probably thinking, hey, we could do all sorts of parameterizations because it wasn't given to us. You're 100% correct. We can do all sorts of parameterizations. Here's one that you're probably all thinking of. T, comma, the square root of 4 minus t squared for negative 2 less than or equal to t less than or equal to positive 2. Now, if you're wondering, okay, why was I thinking that? Well, if you think about the formula for a circle of radius 2, you know that there's that x squared plus y squared equals 4. Solve for y. You would say y squared is 4 minus x squared, and then you have y is the square root of 4 minus x squared. So essentially, you have like an x comma square root of 4 minus x squared. And if you were to use this parameterization, let me just point one thing out here. It would say, start over here, and you move this way. We'll get to why you might care about this in a second. Now, you might be able to detect by my tone of voice, I don't want to do this parameterization. You are correct. You are picking up on my tone of voice correctly. This is not the easiest parameterization because we're dealing with a circle. What's a better parameterization? Yeah, the cosine t sine t is a better parameterization because cosine t sine t, it actually moves a little bit more smoothly. Because it's a circle radius 2, you just need to scale. 2 cosine t, 2 sine t. Where would t need to go between? 0 to pi. Now, if you did this parameterization, which way would you traverse the circle? Left to right or right to left? You'd actually be going right to left. Now, will it make a difference to the final answer whether we have a parameterization that goes left to right versus one that goes right to left? The answer is no, not at this time. So that's a little bit strange because we're so used to thinking like orientation matters. So in the current integrals we're talking about, we're integrating along a curve of some function ds. It doesn't depend on orientation. So we want to get to something in a little bit where it will make a difference, but right now it doesn't. All right. So we're going to go and use this one. If you want to give yourself a challenge, see if this one works out. It probably does, but I'm willing to wager it'll be a little bit more of a headache. So using this one, what would our ds be? Well, ds, a bit of work, and would be 2 dt. It's the same thing we've been doing so far. So I'll skip the bit of work because it's the same thing. You take 2, you go 2 sine t squared plus 2 cosine t squared, square root of that, it turns out. So let's do our y bar. So if I need y bar, what two things do I need to compute? Well, we need mass and a moment with respect to the x-axis. All right, so let's do our mass. So find mass, you integrate along your curve your density function. Because that's how you find mass. Mass is the integral of density. It doesn't matter what setting you're in. Its mass is the integral of density. 1 dimension, 2 dimension, 3 dimension, 4. 5 dimensions, 6 dimensions. I feel like I'm in a Dr. Seuss. I got to break out. All right. So for our case, we're going to use this parameterization. 0 to pi. Our density is y. Okay, in terms of our parameterization, what does that become? 2 sine t, because y corresponds to 2 sine t. And our ds becomes 2 dt. Well, this is not a hard integral. The integral of sine is negative cosine from 0 to pi. When you plug in pi, you get negative 4 times negative 1, which is negative 4 times negative 1. Turns out to be positive 4. Subtract. Negative 4 times cosine of 0 is 1. And if you put this all together, you end up with 8. So y bar is something over 8. But now we need the moment. Okay, so for the moment, and this is the moment with respect to the x-axis, and the reason it's the moment with respect to the x-axis is it's the distance to the x-axis is y, and we're trying to do sort of an averaging of our y's. Okay, so we say, what does this become? Well, 0 to pi, then we have y times another y is really y squared, so it'll become 2 sine t squared. So this is our y squared. And then there's a 2 dt. So how do you integrate something like this? 8 sine squared. What can you do? Half angle? Yeah. Okay. Also known as power reduction. It's too high. This power is too great for us to contain. So what's another way to write sine squared? Well, it turns out it's 1 minus cosine of twice the angle, but then you divide by 2. That's how the 4 came in, because originally I had an 8. If I divide that by 2, that becomes a 4. So the formula I just used, sine squared t is 1 minus cosine of 2t over 2. All right, well, that's not so bad. We can integrate that. So that becomes the integral of 4, which is 4t. Then the integral of cosine will be sine, so we'll have minus. Now there's a 4, but when we integrate here, what else do we need to do? We're going to have to multiply by half, divide by 2 to compensate for this 2 on the inside. So that'll become 2 sine of 2t. Now if you're not convinced that that's right, just go backwards. The derivative of 4t minus 2 times sine of 2t will be 4. Then you're going to get minus 4 cosine 2t. Not quite done yet. What's left for us to do? Evaluate from 0 to pi. And we plug these things in. Well, plug in pi, you get 4 pi. When we plug pi into 2 sine of 2 pi, what do we get? 0. Okay, now plug in 0. 0 times 4, 0. Plug 0 into sine, 0. So our m sub x is 4 pi. So that goes here, 4 pi. And therefore, our y bar is pi over 2. Well, what is that? Well, pi is about 3.14, so pi over 2 is about 1.57. Which would put us, if this is 0 to 2, that would say right around there is our center of mass. Now, is that reasonable? And I think it is, because if we think about it, we said we're heavy near the top. So we should definitely be closer to the top. And you might say, but wait a second, our center of mass isn't actually on our object. That's okay, because this is an object with essentially holes in it, more or less. It's all right. If our center of mass had been up here, way above 2, say at pi, what would we do? Yeah, we'd look for our mistake. Because the center of mass can't have everything be on one side of it. It has to somehow be in the center. Here it's reasonable in that if you think about it, there's a lot of mass above, and there's actually a fair amount of mass below because there's a lot more space below. All right, well, let's talk about work. Now, how do you compute work? We know how to compute work if we have force and distance. And then we said, you know, we can actually go one step further, where work is not just force times distance, because that's just a really simple understanding of physics. We can introduce vectors into this and say work is the dot product of the force vector and this displacement vector. So D is how much the object that's being acted on moved. So it has sort of two components to it. In which direction did it move and how much did it move? So that's how we can compute work. We say, okay, well, what if we do the following? What if I want to push something along a curve? And figure out how much work I have. So I have this curve, and here's my curve, and I'm sort of, you can imagine I'm pushing this object along this curve, and I want to know how much work does it take for me to move that object along that curve. And what's going to happen, of course, is that on some points in that curve, there's going to require more force, and in other places it might require less force, and I just want to know what's the total work. So that's our goal. Well, the answer is we do what we always do whenever we're trying to we're faced with this kind of a question. We say, okay, let's not try to move the object all at once. Let's just move the object from here to there. In other words, it's just a little teeny tiny change. A small change, but an important one. So why? Well, because it's a small change, what happens is that I can treat force as being constant. It doesn't change significantly, so I can say, all right, now I can treat it as I would a constant. And similarly, I can talk about my displacement, which is this part downstairs. That is also, I can treat it like a straight piece of a line segment. So I get the following. So work is the sum of the following. At each point I take the force at that point, and I'm going to dot it with T delta S. Well, what's happening? T, well, remember what T is. T is your tangential vector. Okay? So if I come along here, let's move to a point a little bit further away. So if I'm at this point right here, your T is the unit vector which is tangent to the curve. So essentially that T there is giving us a direction. So T is for direction. Now, I also need to know a distance, and that is coming from the delta S. And once you have those two pieces, a direction and a distance, that gives you your displacement, a vector. So we get that, we have the integral along the curve of F dot T ds. Okay. So that's the basic idea. Now, how do we actually do it? Well, let's recall a little bit about our t, our vector t. So suppose I have a parameterization, and I'll call it r of t, which is x of t, y of t. I'm going back into my vector setting because I want to be in something where I can do calculus at. In particular, some place where I can take derivatives. So we say, all right, so if I want to find my tangent, I take r prime divided by the magnitude of r prime. So that would be x prime of t, y prime of t, that's r prime. And then the magnitude of r prime is the square root of x prime squared plus y prime squared. And you're like, ah, another one? Another one? We already had one. Because we had that ds is a square root of x prime squared plus y prime squared. Now you're telling me there's a second one? But this is the great news. Because look where they're at. See, one of them is in a denominator. Where's the other one? It's in the numerator. What's going to happen to those terms? They cancel. Oh, happy days. Happy days. So when we take t ds, the square roots go away, and we're just left with x prime of t, y prime of t dt. This is sometimes called dr, and the individual pieces, x prime t dt and y prime t dt, sometimes you'll see that referred to as dx and dy. So, here you go. When we talk about work, we'll have a force. So there's this force thing, m and n. And we're going to integrate along our curve. Whoa, I'm sorry. Integrate along our curve, f dot t ds. Well, that will become the integral along the curve of f dot dr, because this is what we mean when we say dr. But oftentimes you'll see this written as integral along our curve of m dx plus n dy. And when you see m dx plus n dy, what you're really referring to is the m and n are your aspects of your force vector, and your dx dy are your x prime t dt and your y prime t dt. So what happens is you might look at this and you might say, oh my gosh, because what you'll see here is really when we talk about m, we're really talking about m as a function of x, y, dx. And when we talk about n, that's again, it's a function of x, y, dy. And so you might think, oh, this is multivariable, but everything reduces down to your parameterization. It's still single variable. Okay. Now, there is the question, does this idea work in higher dimensions? And the answer is absolutely. Oh, I'm very tilted here. I'm sorry about that. The same idea works in higher dimensions. It carries over exactly as you would expect. Now, there's this comment at the bottom. I want to point this out. This integral, it does depend on the way we travel. See, previously when we talked about the curve where we had that wire, we said, look, does it matter which way we travel? And the answer is no, it doesn't. But now when we talk about this force, it will depend. It matters which way we move on the curve. And you might say, well, how did it all of a sudden spontaneously matter? And the reason it spontaneously mattered was because of t. Because remember, what is t? T is talking about the direction of motion. So t, if I'm moving on this curve, in say from left to right, t would point in this direction. If I reverse my orientation, what happens to t? It would point in the opposite direction. So when you reverse orientation, you negate your t, which means you flip the sign. So that's why when you're doing force, it does make a difference. It does make a small difference. So let's do an interesting example. Something that's not a circle. So, after a heavy snowstorm, you decide to build a small fort in preparation for a snowball fight with some friends. The fort consists of a curved wall built out of snow to offer something to hide behind. The wall you build will lie on top of the curve C, where x of t, y of t is 3t squared, comma, 2 root 3 t cubed, where 0 is less than or equal to t, less than or equal to 1, and distances are measured in feet. The height of the wall at a given xy is a half x plus 5/2 feet. You will need 1 cubic foot of snow for each square foot of surface area of the wall. And we want to use a line integral to determine how many cubic feet of snow we'll need to build this wall. So what's going on here? Well, sort of the basic idea here is we have the following. We have this curve here. I don't know what this curve is doing. It's doing something. So let's say our curve is doing, I don't know, some sort of, here's our curve C. And what's happening is that over this curve, we're going to build height. Now, it's not going to be very high near the origin, but as we go further out, it's going to get higher and higher. So we have this increasing height for this wall. And, of course, what will happen is we're going to be hiding behind this wall. So what we need to do is figure out the total height here. Or rather, if you will, what's the area here? Because the area will correspond to how much snow we need. So this particular problem, we can rephrase it in the following way. We want to do the integral along the curve of 1/2 x plus 5/2 ds. Okay, so that's what we need. That'll tell us the total amount of area, and the area corresponds to how much cubic feet of snow. So, well, let's start by finding ourselves our ds. So ds, that's the square root of x prime squared plus y prime squared dt. So, let's see. Come here. X of t is 3t squared. And the derivative of that will be 6 times t squared plus y prime of t is 2 times square root of 3 t cubed. So the derivative of that will become 6 times square root of 3 times t squared, and then of course we're going to square that dt. Now one of the things we can do to make our lives a little bit easier is say, hey, wait a second, both these terms have a 6t in them. So we could actually factor out 6t quantities squared. And if we did, we'd be left with 1 from the first term. And from the second term, because we factored out 6t, we're left with the square root of 3t, and that's being squared. So plus 3t squared dt, or if you like, 6t times the square root of 1 plus 3t squared dt. Now at this point we're probably like, that is a little different. And different could be fun. Alright, so let's see what happens now. So, when we're doing a line integral, we're really going to turn everything into our parameterization. So, our parameterization has time going from 0 to 1. 0 to 1. Everywhere I see an x, I'll replace it by 3t squared. So I have 3/2 t squared. And if there were a y, I would replace it by the corresponding y term, but there is no y, so that's all right. And then the ds becomes our 6t square root 1 plus 3t squared dt. Now at this point you might say, okay, why don't we just multiply it all out? Life is good. However, we have a square root. So when we have a square root, we want to be sort of a little bit cautious and think about how do we handle it. Well, our best way to handle a square root is if we can't get rid of it, we do a substitution. So let's plan that. Suppose we make u be what's currently inside the square root. Well, what would du be? Well, the derivative would be 6t dt. Very conveniently, we have a 6t dt. All right, so that's good. Now, there is one small catch. Well, there's always got to be one, right? Notice we have this other part here. Now, we can do a little bit. Notice what we have. We have 1/2 times 3t squared plus 5/2. The reason we do that, notice that we currently have, let's do it to the side here, u is 1 plus 3t squared. So, 3t squared is u minus 1. So we can rewrite this as 1/2 times u minus 1 plus 5/2. Or if you like, 1/2 u, then minus 1/2 plus 5/2 would be plus 4/2, or plus 2. So, that's how we can replace that expression. So what do we have? Let's update everything. So after making that substitution, we'll have the integral. This part becomes 1/2 u plus 2. The 6t dt becomes the du. Square root of 1 plus 3t squared becomes square root of u. Since we're calculus, we'll write that as u to the half. And now, don't forget the bounds. These bounds our t-bounds up here. We need u-bounds. Well, that's not too hard. Put in t equals 0 into our expression for u. We'll get u equals 1. Put in t equals 1 into our expression for u, and we'll get u equals 4. Now, this looks like it might be integrable. Closer anyways. Multiply the u to the 1/2 through. So you get 1/2, u times u to the 1/2 is u to the 3/2. And then plus 2u to the 1/2. That's definitely something you can integrate. So what do we get? The first term will have 1/2. We're going to have u to the 5/2, 3/2 plus 1, multiplied by the reciprocal, 2/5. Then the second term will have u to the 3/2. You add 1 to the exponent, multiplied by the reciprocal, 2/3. And now we're going to evaluate from 1 to 4. Well, of course, before we evaluate, we should simplify. 1/5 u to the 5/2 plus 4/3 u to the 3/2 from 1 to 4. So we plug in 4. Now we could do a couple of options. We could say, well, 4 to the 5th, well, that's 1,024. Then we could say, okay, square root of 1,024 is 32. Now that's probably not what we want to do. That sounds like work. So really we should think of this as first to the 1/2. That would be square root of 4 is 2. Then take that to the 5th power. 2 to the 5th, 32. So we get 32 over 5. The next term, square root of 2, is going to be 2. Cube it, 8 times 4/3. 32 over 3. And we're going to subtract, well, 1 over 5 plus 4 over 3. All right. Well, common denominator would be 15. So we get 96 over 15 plus 160 over 15 minus 3 over 15 minus 20 over 15. And you're probably wondering, where did that minus come from? Well, don't forget, that minus goes through. Okay, 96 plus 160 is 256. Subtract 3, that's 253. Subtract 20 will give us 233 divided by 15. And that is how much feet we need. So this is our cubic feet. Now, is it reasonable? Well, it's not so bad. If you think of 15 squared, 15 times 15, that's 225. So this is roughly speaking close to 15.5 cubic feet of snow. Now, if we think about the picture here, how wide is this, or how long is this? Well, we didn't actually compute that, but we know we start at the origin, because when you plug in 0, you get 0, 0. And out here, when you plug in t equals 1, you're at 3 and 2 root 3. So that's at least 3, probably closer to 4, maybe even 5 feet out. On the other hand, notice that as we move further out, our height goes from 1/2, and by the time we reach over here, we're all the way up to what? Well, that'd be 3/2, 4 feet almost. So yeah, about 15, that's not so bad. That seems pretty reasonable based on the problem. So there you go. All right. So look, not everything has to work out perfectly. You can still do stuff. We can still handle square roots when we have unusual terms. Now, since it appears we have a little bit of time, let's jump back to this problem. Because when we did this problem, we said, well, let's do the circle using the cosine and the sine. And let's just sort of like, not deal with that. And I said, well, we'd get the same answer. Let's find out if that's a true statement. Okay, so let's do this piece here. I want to repeat this problem, but let's do, instead, this parameterization. So let's start by our ds. So ds is the square root. You take x prime squared, well, that'll be 1 squared, and y prime. So think of this as square root of 4 minus t squared. That's 4 minus t squared to the half. So the half comes down, 4 minus t squared to the minus a half, then times the dirt of the inside, which is minus 2t, and all that's being squared. Now, if you look at this for a minute, and you probably want to spend at least a very minimum at least a minute, the 2's cancel. The minus won't matter when we square it, so we get a t squared upstairs, and because of the minus, this goes downstairs as 4 minus t squared. Well, I can now put these together, and notice I can get a common denominator of 4 minus t squared. So I get 4 minus t squared from the first term, plus t squared, over 4 minus t squared. Well, that's not so bad. Upstairs, the t squareds cancel, and so we end up with 2 over square root 4 minus t squared dt. So, let's do our mass. So mass is the integral along our curve of our density. So what's our density? Well, our density is y ds. So negative 2 to positive 2, our y is square root 4 minus t squared. Our ds is 2 over square root 4 minus t squared dt. Well, those cancel. So it's just integrating 2. That's not so bad. Indeed, this becomes 2t. If I went from negative 2 to positive 2, which will be 4 minus negative 4, which is 8. Notice it's the same as before. Coincidence? No, of course not. Of course not. Now, let's do the m sub x. So, what is m sub x? Well, as before, integral on the curve, it's still y times our density, which is y again, ds. Now you're thinking, aha, this is the one. This is the one that's going to get us in trouble. Negative 2 to 2, that's square root of 4 minus t squared, then another square root of 4 minus t squared, there's a y, there's the second y, and then 2 over square root of 4 minus t squared dt. Again, we get the cancellation. The 2 will come out. So this is 2, integral negative 2 to 2, square root of 4 minus t squared dt. And now you're like, ha, you are stuck. You can't integrate that. Or can you? Well, remember, integrals represent things, but we're allowed to interpret it however is convenient. Now, in this particular thing, what we can say is, let's interpret this integral as it were an area. So, I am perfectly allowed to do that. So what's happening is that this integral corresponds to finding the area of that curve. Well, that's half of a circle of radius 2. So, this integral is 1/2 of pi 2 squared. And therefore, we get that our total for m sub x is going to be 4 pi. Look, same as before. And so, finally, y bar is m sub x over m, which gives us 4 pi over 8, which is pi over 2. So maybe it's not so bad to try it in a different way. But notice, it doesn't matter which parameterization we used. We still got the same answer. So, whatever you use, make sure it's something you're comfortable with, and be willing to try different things. You never know. Maybe some things aren't quite as bad as they look. Well, not always. All right, that's it for now. Come back next time, because it's going to be beautiful. Back to the fundamental theorem of calculus. Great ideas. Great ideas. All right. Bye.